Okay, YouTube, this is my second video on a module in which we are plotting complex numbers, and what we're going to do in this video is explore this concept of an absolute value. And so I suppose we'll start with recalling the fact that the absolute value of a number is the distance from that number to 0 on a number line. And so if we said, the absolute value of -3 or the absolute value of 3, with respect to its geometric representation, we say 3 is 3 units away from our 0 marker, but so is -3. When we're discussing a distance, of course, we would refer to distances as always being positive. And so using this very same definition here, we're going to define the absolute value of some complex number, z, where z is equal to some a plus bi. And so we'd say that the absolute value of a complex number z, of course z is a plus bi, we say is denoted by this here. And we'd say that the absolute value of a number, okay, absolute value of z, is written the same way you'd write the absolute value of any other number. So I do want to write this also. It's the absolute value of a plus bi. And in order to find this, what we're going to do is we're going to use a geometric interpretation. And so starting with graphing this point, certainly we could see that if this is the point AB, then we would have gone to the right A units and upward B units. But in terms of where the absolute value would lie, you could see that in this diagram right here, it is this blue segment. And the reason why we refer to this blue segment as our absolute value is because this point right here really is the complex number, I'll call it Z naught, Z0. But we'd say that this is 0 plus 0i, or really it represents 0 as a complex number. And so basically, we're finding the distance from this point back to the origin. The way we're going to do this is by using our Pythagorean relationship here. And so we're going to say that the absolute value of our complex number here, if we were to represent this way, we'd say the absolute value of our complex number, that would be this distance. If we were to square that, okay, that would be equal to a squared plus b squared, where these were the components of our complex number in the first place, the real part and the imaginary part. And so solving for the absolute value of z, you could see that taking the square root of both sides of this relationship here, this equation, we get that the absolute value of z should always be equal to the square root of the sum of the squares of the legs of our triangle. So we say by definition, and this is a formula worth remembering starting like right now, we would say that the absolute value of a complex number a plus bi really is the absolute value of z, which is the absolute value of a plus bi, which is the square root of a squared plus b squared. So with these examples here, what I want to do is I want to make sure we write a note here, always sketch a picture. And the reason why is because I get plenty of people that remember this formula just fine, but when you sketch a picture of your complex number, and at least in rectangular form to begin with, you can see the relationships that exist with Pythagoras here. And so let's start with looking at letter A here. We want to determine the absolute value of these complex numbers. So the absolute value of z, okay, this would be the same thing as the absolute value of 3 plus 4i. The idea here is that we just want to know what the values of a and b are. And in this case, of course, we have 3 and 4 respectively. So when I say sketch a picture, what I mean is get an idea of what quadrant you're in, okay? Also, not that it matters here, but also, set up your right triangle here. And really that's what it is that we're setting up. And so we say that if we know that this is 3, 4 here, then our absolute value is this distance right here. This is our absolute value of z. And we already know this is 3 and this is 4. And so with this absolute value right here, we're going to go ahead and say that the absolute value of z, just using Pythagoras, should be the square root of 3 squared plus 4 squared. And so simplifying this, what we discover is that we get 9 plus 16 in here, which comes out to be, in this case, a perfect square. And so since we took the square root of 25, we get plus or minus 5. The last thing we have to discuss basically is the fact that this cannot be negative. And the reason why is because even though we took a square root, this is a distance that we are finding. So we say that this distance back to the origin here is just 5. You can also see that this is really just solving for the hypotenuse length on a right triangle situation. So really quickly here with this second one, let's just go ahead and do this first. We say z, if we want the absolute value of this, we would get the square root of -1 squared plus -2 squared. And simplifying this out, suppose -1 squared is 1, -2 squared is 4, we really get the square root of 5. And so let's now sketch our image. And I know I did this one backwards, but I wanted you to see something here. If we go left 1 and down 2, that would be, of course, that point right there. There's our complex number z. But we would say, looking at this triangle here, we have -2 and a -1. And what we ended up with here was the absolute value of z being the square root of 5. And we can see that that's entirely reasonable given the case that we're looking for the hypotenuse on a right triangle. So here's what I'd like for you to do. Go ahead and pause the video and graph these two complex numbers, but then go find their complex numbers. When you're ready to see their solutions, go ahead and unpause the video here. But if you're ready to see these solutions, we'd say that we get a is 5, b is 12 here. So our absolute value of z is just the square root of 5 squared plus 12 squared. And so we get the square root of 25 plus 144, which does in fact come out to be the square root of 169, which does in fact come out to be plus or minus 13. But this is fabulous because we just had a perfect square 169 in here. Now looking at this sketch here, this is a little bit different. If I asked you to go sketch 512, it's just really not that desirable to make all those notch marks. And so, we could say that maybe, we're going by 2s or 5s itself. But we could say that if I were, say, maybe going by 5s here, I say that this is 10, 5, 10. Here, we could see that 5, 12 would have just been a little bit north of 10 here. And so our right triangle comes from this situation here where we're saying that this is 5 and this is 10, and that our square root of 169 came out to be 13. This is a 5, and sorry, this is not a 10, this is a 12 here. It's a 12. But a 5, 12, 13 triangle. Now looking at this last one here, if you went ahead and sketched this out, you saw that we would be going 2 to the right and 3 down. And so, discussing a triangular situation here, this is the point 2 minus 3i. To find its absolute value, we're finding this distance back to the origin. Let's drop our altitude back up here and say that we know that this is 2 and this is negative 3. And so again, we'd say the absolute value of our z here, the absolute value of z, would be the square root of 2 squared plus negative 3 squared, which simplifies out to be the square root of 4 plus 9 and the square root of 13. And we would just leave it that way. We'd say the absolute value of z is root 13. And we could certainly put this into a calculator and get a distance on it if we were to take the square root of 13, just to talk about reasonability here. Square root of 13, we had about 3.6. And so to say this is approximately 3.6, given that we had 2 and 3 as our legs of our triangle, would be entirely reasonable. So that's how we find the absolute value of a complex number. Cheers.